All right, so first, what is a rational expression? A rational expression is an expression of the form P equals Q, where P and Q are polynomials. So let's just take into polynomial expressions and dividing. That gives us a rational expression. The only restriction we have is that, as with always when we're dividing, our denominator, Q, cannot be equal to 0. Okay, what are some examples of what rational expressions look like? So for example 1 here, it says, determine whether the following expressions are rational. In order to be rational, the numerator has to be a polynomial and the denominator has to be a polynomial. For part A, x minus 3 over 2x. X minus 3 is a polynomial, it's linear. 2x is a polynomial, again, it's linear. So when we divide those two, we get a rational expression. So yes, this one, x minus 3 over 2x is rational. Yes, it's rational. Moving on to part B, we have 2 square root of x minus 3 over 2x minus 1. This is not rational. The square root of x gives us a problem. Remember, in order to be a polynomial, our x has to be raised to an integer power, positive integer power. So if we have something like x squared or x cubed or x to the 10th, that's fine. But the square root is x to the 1/2. That means that that's not a polynomial, which in turn means that this is not a rational expression. So B does not work. Okay. For part C, we have 6x plus 5. That is fine. That is a line or linear. And then we have x to the negative first power plus x minus 12. Almost, but in the denominator here, no. In the denominator here, we end up with a negative exponent. We can't have a negative exponent on our x. Remember, our exponents have to be non-negative integers. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, and so on. So part C is not a rational expression, but something like part D is 6 divided by x squared minus 4. That is a rational expression. So again, polynomial divided by polynomial gives you a rational expression. Now that we know how to identify a rational expression, it's really important for us to be able to determine where a rational expression is defined, or if it's a function, where a rational function has a domain. The biggest thing we need to worry about is our denominator. When we have a denominator, we have to make sure that that denominator is not equal to 0. So for a rational expression, we will say that it's defined everywhere except where the denominator is equal to 0. So to find the points where it's undefined, we have 2 steps here. We set the denominator equal to 0 and then solve the equation. Usually setting our denominator equal to 0, since the denominator will be a polynomial, that'll involve us doing a little bit of factoring. So set the denominator to 0, factor, find the solutions to the zeros of the denominator, and that tells us where our function is undefined. All right, so looking at the expressions that we have here in example 2. 7, it says determine the values for which the rational expression is undefined. We need to look at the denominator. What makes the denominator 0? That's where our rational expression is undefined. So we'll take our denominator for the first expression, 7x squared minus 3 over 2x. Take 2x, set it equal to 0. That tells us that x is equal to 0. So this function, or this expression, I should say, is undefined at x equals 0. And just to be clear about what that means, what does it mean to be undefined at x equals 0? That means that if we plug in 0 to the expression, we do not get an answer out, because we literally have something over 0 and we can't divide by 0. That doesn't make any practical sense to us. So there's no output associated with x equals 0. All right, for our next expression, we have 3. 3x minus 1 equals 0. So 3x equals 1. And x equals 1/3 would be the 0 of the denominator. So this one is undefined at x equals 1/3. And for the last one, we have a little bit of work to do there. So for x plus 5 over x squared plus x minus 12, x squared plus x minus 12 can be factored to x plus 4 times x minus 3. And if we set that equal to 0, that gives us the factors of x plus 4 equals 0 and x minus 3 equals 0. So x equals -4 and x equals +3. So our function is undefined at -4 and +3. All right, so rational expressions are polynomials divided by polynomials. We know that polynomial functions are defined everywhere. So rational expressions are defined almost everywhere. We just have to make sure that the denominator is not 0. So to find the places where our function is undefined, a rational expression is undefined, we set the denominator equal to 0 and solve for x. Moving on. So for C and D, take a moment to set the denominator equal to 0, factor and solve to figure out where these two expressions are undefined. All right, so let's see. We have 4x minus x cubed equal to 0. We can factor out an x from both of these expressions. And that gives us x times 4 minus x squared equals 0. 4 is 2 squared and x squared is x squared. So this is a difference of squares, which factors to 2 minus x times 2 plus x equals 0. So then we'll have x equals 0. That's one solution. 2 minus x equals 0. So 2 is equal to x, or x equals 2. And then 2 plus x equals 0. So x equals -2. Then let's move on to part D. So for x squared plus 5 equals 0, how can we factor this? The answer is you cannot factor this. So this is prime, which means that there are no places where the function is undefined. So it's not possible to make that denominator 0. That means that this expression is defined everywhere. Or we'll say defined for all real numbers. All right, so again, for rational expressions, polynomial divided by a polynomial, they are defined everywhere except for the zeros of our denominator. And if there are no numbers that make your denominator 0, well, that just means that the expression is defined everywhere. You can pick anything for x. All right, let's move on to the next thing. Now, this is a very subtle difference. We're going to next talk about rational functions, evaluating rational functions, and then finding the domain of a rational function. The difference is now we're taking rational expressions and putting them in function notation. And where we said that a rational expression is undefined, that same technique will help us write out the domain of a rational function. Okay. We'll just have to write an interval notation, which we'll talk about in a second. So what is a rational function? A rational function is r of x equals p of x over q of x, where p and q are polynomials and q can't be 0. So two polynomial functions being divided. Same thing we did before. The next example asks us to evaluate the rational function r of x equals x minus 1 over x minus 5 at 3, 1, and 5. Just as before, to evaluate a function, you plug the number in parentheses into the function for x. So r of 3, this is equal to 3 minus 1 over 3 minus 5, which is -2 over -2. Oh, +2, sorry. +2 over -2, which is -1. What does this mean? When x is equal to 3, y is equal to -1, the point 3, -1 is on the graph of this rational function. There's a few different ways that you can think about this. All right, but that's it. We found the answer. R of 3 equals -1. For R of 1, we'll have 1 minus 1 over 1 minus 5. 1 minus 1 is 0. 1 minus 5 is -4. 0 divided by -4 is just 0. So this tells us that 1, 0 is a point on the graph. 1, 0 would be on the x-axis, actually. So that would be an x-intercept. All right, and last one, just going to scroll over to give us a little bit more space. R of 5, that's 5 minus 1 over 5 minus 5. Doom, doom, doom. This gives us 4 over 0. Remember, we cannot divide by 0, so 4 minus 0 is undefined. What does this mean? We can't plug in 5. The function is not defined at 5, so there is no output at 5. When we think about, I'll show you what the graph of this function looks like in a minute, but on the graph never crosses x equals 5. There's no point that corresponds to x being equal to 5. What we just showed in the last part where we found that at x equals 5, r of x was undefined, we would say then that 5 is not in the domain of the function r of x, okay? The domain of a rational function is the values for, would be all x values except the ones that make our denominator 0. So all x values for which q of x is not equal to 0. So to find the domain, you really want to think about what's not in the domain. Take your denominator, set it equal to 0, solve. That tells you the numbers that are not in the domain. And we're going to practice writing out our domain in interval notation. All right. First problem. Well, I'll show you this one that's already done for us. We have 1 over x. Okay, that's the most basic rational function we can look at. For 1 over x, our denominator is x, so x cannot be equal to 0. What does that mean? We can plug in literally any other number for x other than 0. So when we write out our domain, we want the domain to show all of the real numbers except 0. That means we're going to break up our intervals at 0. We get -infinity to 0 union 0 to infinity. There are parentheses around the 0 to indicate the 0 is not included, but everything else is included in the domain. In words, we say that this is all real numbers except 0. And in interval notation, which we're going to want to know how to use, that's -infinity to 0 union 0 to infinity. We're going to scroll down and practice some of these. Oh, this is nice. This is what the graph looks like. So we're going to practice some of those in the next section. Before I go on, this is the graph of 1 over x. What we have actually going on at x equals 0. That's the y-axis, x equals 0. Notice the graph kind of curves once it gets close to 0. On the right-hand side, it goes up to infinity. On the left-hand side, it goes down to -infinity, okay? This is called an asymptote. We'll talk about that a little bit later in the chapter, but yeah, on our points where our function is undefined, we usually end up getting something like this. That's an asymptote. Sometimes we also get something else called a hole, but I just want to show you visually what it looks like or what it means for our function to not be defined at a point. All right, so what do we do to determine the domain of our function? To determine the domain of a rational function is exactly the same as what we did to determine where a rational expression is undefined. Set your denominator equal to 0, solve for 0. The only difference is now we want to write our domain in interval notation. We'll take those zeros of the denominator and break up the intervals at those points so that they are excluded. So for each of these, we are going to take the denominator, set it equal to 0, solve, and then write our domain and interval notation. For A, we have 3x plus 5 equals 0. That means 3x is equal to -5. Or we can say for the domain, 3x plus 5 cannot be equal to 0. 3x is not equal to -5, and that means that x should not be equal to -5/3. So our domain would be, in words, all real numbers except x equals -5/3. We want to write this, though, in interval notation. In interval notation, we'll break up the interval at -5/3. So we'll say it's -infinity to -5/3, close that, union -5/3 to infinity. All right, that's for A. For part B, we have x squared minus 36 equals 0. This is a difference of squares. So it factors to x plus 6 times x minus 6 equals 0. And we actually end up getting 2 points here. X can't be equal to 6. I'm sorry, -6. And x can't be equal to +6. So what does this mean? When we write out our domain in interval notation, it would be all real numbers except 6 and -6. So we have to break up the number line in two places. Starting at -infinity, of course, we go from least to greatest. So we'll go to -6, break up the number line here, then union, pick back up at -6, go to 6, close again, and then union 6 to infinity. Okay, so at every point where our denominator is 0, we break up the intervals to create our interval notation. All right, part C. We have r of x is 2x plus 5 over 4x minus x squared. So 4x minus x squared, if we set that equal to 0, gives us set x times 4 minus x equals 0. So x equals 0 and x equals 4. These are the two numbers that would make our denominator 0. That means that the domain is all real numbers except these two. So we would have -infinity to 0, union 0 to infinity. I'm sorry, union 0 to 4, and then union 4 to infinity. Last one, part D, m of x is equal to x minus 3 over x squared plus 100. This one is actually going to be quick. So if we try to factor or set the denominator equal to 0, x squared plus 100 equals 0. This has no solution because it's prime. So that means that there are no numbers that make the denominator 0, which means that there are no points where the function is undefined. So the domain would be all real numbers. And in interval notation, that's just -infinity to infinity. All right, so now we know what a rational function looks like. We know how to evaluate rational functions, and we know how to find the domain of a rational function. That's the last topic that you learn in section 6.1. So we can move on to 6.2, where we talk about multiplying and dividing rational expressions. Before we jump into rational expressions, let's just recall how we multiply and divide any fractions. So for multiplying two fractions, well, what's that? I'll write at the top here, recall. To multiply fractions, we just multiply the numerators and the denominators. So if we have a over b times c over d, that equals a times c over b times d. If it's possible to simplify after we multiply, then we would simplify. Okay, so multiplying is the easiest operation. You multiply the tops, you multiply the bottoms. That's it. The rest of the operations aren't that easy, but division isn't so bad. So divide fractions. You may have learned the little phrase, keep, change, flip. You change the problem into a multiplication problem by keeping the first fraction the same and then multiplying by the reciprocal of the second fraction. So A over B divided by C over D would be equal to A over B times D over C. Remember, the reciprocal of a fraction means we're flipping the fraction. So keep the first fraction the same, change the division to multiplication, and then flip or take the reciprocal of the second fraction. And then that equals A times D over B times C. Okay. And then the last thing that we need to remember before we jump into this section is how to simplify fractions. To simplify fractions, we use the equivalent fraction property, and we cancel out any common factors in the numerator or denominator. So what does this mean? If we have A times C over B times C, like we have written here, we can just cancel out those C's, and that's the same thing as A over B. All right, so we're going to practice simplifying, multiplying, and dividing rational expressions. The difference is now, instead of just having a couple numbers like, 1/2 times 3/5, our fractions are going to be algebraic fractions because they're going to include x's. Okay, we might have to, or we do need to, factor each numerator and denominator as much as possible, and then use these techniques: multiply the numerators and multiply the denominators, or keep, change, flip to multiply and divide where appropriate. All right, first we're going to do some problems where we practice simplifying rational expressions. To simplify rational expressions, we'll follow these 3 steps. For pretty much all of these problems, you're going to start off by factoring. Factor each numerator and denominator completely. Okay, once you factor your numerators and denominators completely, if there are any common factors, we want to cancel those out. And then after we cancel the common factors, we will, we're done. Cancel out the common factors, write out what's left in your numerator and what's left in your denominator, and that's your final answer. And we keep the final answer in factored form. All right, ooh, look at all of these. I mean, they're so good. So for problem A, we have a rational expression, 36xy over 2xy. This is rational because even though we have different variables, the variables have exponents that are integers, positive integers, so this works. For something like this, where you just have numbers and variables, or just single variables in your terms, the easiest way to do this would be to factor the numerical part as much as possible. Writing out a prime factorization would work. You could also think about divisibility. What number divides 36 and 2? Or you can just say, oh, 36 divided by 2 is 2. In the book, it shows, if you look down at the solution for A, it shows this by factoring out the 36 as much as possible. That's the way that I would recommend doing it, but for some of you, you might prefer using the division method for simplifying. That is fine. But if we factor the numerator as much as possible, since this one is shown, we'll just look down here. We see 36 is 2 times 2 times 2 times 3 times 3. You could have also said it's 2 times 18, and the 2 will cancel out with the 2 in the denominator. Then we have an x in a numerator and an x in the denominator, so those cancel out. And then the y in a numerator and the y in a denominator cancel out. When we're done canceling all this stuff, and then we have 36 divided by 2, that equals 18. All right, that was the easy one. For the rest of these, we can use our factoring techniques to factor the numerators and denominators. For part B, x squared minus 4x over 3x minus 12. The numerator factors to x times x minus 4, and the denominator factors to 3 times x minus 4. We see here that both of these terms have both the numerator and denominator have an x minus 4 in common. So we'll cancel that out. And our final answer is what's left, We're left with x over 3. That's it for part B. For part C, 10 plus 5x. This would be, might be easier to write it this way. 5 times 2 plus x over 2 times x plus 2. Then you have to ask yourself, is 2 plus x the same thing as x plus 2? Yes, because those are being added. So those two terms are actually the same. We can cancel them out. And then we're just left with a 5 in our numerator and a 2 in our denominator. So 5 halves. All right, last one. X squared minus 5x plus 6 over x squared minus 6x plus 8. So we have two trinomials here. They're going to factor to binomials. In the numerator, we get x minus 2 times x plus 3. And in our denominator, we get x minus 4 times x minus 2. So we see here now in factored form that the numerator and denominator both have an x minus 2. So then this leaves us with x plus 3 over x minus 4. Now, occasionally a student might get to this step and then they say, oh, and I can cancel the x's. And then I cry because we can't cancel the x's in this example because the x in the numerator is being added to the 3. The x in the denominator is being, well, there's a 4 being subtracted from it. Those are not being multiplied. You can only cancel factors. Factors are things that are being multiplied. Those are being added and subtracted. We can't break them up. All right, so this is our final answer for this problem. This is a nice little note. If we have opposite terms being subtracted, a minus b and b minus a, those are opposites. When we divide them, we get -1. I also want you to note that b minus a is just equal to negative a minus b. That'll help you with factoring. Again, let's jump down to the multiplying. To multiply rational expressions, you want to, well, technically you multiply the numerators together and multiply the denominators together. The easiest way to make sure that you are multiplying and canceling out and simplifying as much as possible is to first factor each numerator and denominator. Then if there are common factors in either numerator with either denominator, cancel those common factors, and then at the end, multiply what's remaining. We have 3 practice problems here. For A, we have 7a minus 14 over 2 plus a times 3 over 3a minus 6. We want to factor each numerator and denominator as much as possible. This would be 7 times a minus 2 over a plus 2 times 3 over 3 times a minus 2. And then you want to see if there are common factors in either numerator with either denominator. It doesn't have to be the same numerator and denominator being canceled. You can cancel something in the first numerator and the second denominator. That's fine. So for here, we see that 3 can be canceled out. That's easy. But also, the first expression has an a minus 2 in the numerator. The second one has an a minus 2 in the denominator. So we can cancel those. And then what are we left with? We're left with 7 in the numerator and a plus 2 in the denominator, and that's it. So the solution here would be 7 over a plus 2. On to B. For 4m over m squared plus 5m plus 6 times m squared minus 4 over 8. Uh-oh, I almost erased the problem there. I think it was just an 8, okay? Wait, there might have been more. No, I think it's just 8. For this one, what did I do? There we go. For this one, when we factor in the numerator, there's not much to factor. It's just the 4 times an m, that's it. In the denominator, m squared plus 5m plus 6 can be factored to, oh, I did miss something, sorry. I had to check the PDF. That was an 8m, so let's fix it back. I accidentally erased it when I was erasing the solutions. All right, so for our first denominator, we get m plus 2 times m plus 3. For the second numerator, m squared minus 4 factors to m plus 2 times m minus 2. And then for the denominator, 8 times m, we can write that as 4 times 2 times m. All right, now things are factored. What can we cancel out? There's lots of stuff here that cancels out. Canceling is my favorite part. Let's see, we can cancel the 4 in the numerator with the 4 in the denominator. We can cancel out the m in the numerator with the m in the denominator. And we can cancel out the m plus 2 with the m plus 2. Remember, you can only cancel terms if it's one in the numerator and one in the denominator, not 2 numerators or 2 denominators. All right, then what's left? We're left with m minus 2 over m plus 3. And there's another 2. So 2 times m plus 3 in the denominator. Sometimes when I go through this, after we do the canceling, there'll be a lot of stuff there and a lot of canceling. I go through and I circle what's left just to make sure I don't miss anything in the final answer. All right, and last one. We have 6a squared over a squared plus 10a plus 24. That would be 6 is 2 times 3. A squared is a times a. And then over a squared plus 10a plus 24 is a plus 6 times a plus 4. For the second expression, a squared minus 36 factors to a plus 6 times a minus 6. And then 18 would be 6 times 3, so 2 times 3 times 3. We have times an a there. All right, now for my favorite part. What cancels? Well, the a plus 6's cancel. We can cancel out one of the 2, the 1, 2, and one of the 3's, and one of these a's. All right, and what are we left with? We have an a in the numerator and an a minus 6 in the numerator, an a plus 4 in the denominator, and a 3 in the denominator. So that would be a times a plus 6, a times a minus 6, I'm sorry, and you can leave it in factor form. Over 3 times a plus 4. All right, then next I want to go on to the practice problems for dividing rational expressions. Remember, for dividing, we have to, if we divide 2 fractions, change the division problem into a multiplication problem by doing keep, change, flip. So that's what first step is. Multiply the first expression by the reciprocal of the second one. We'll write this as a over b times d over c. And then from here, we do the same steps that we did for multiplying. Factor the numerators and denominators, cancel out any common factors, so simplify, and then multiply what's left. So when we are doing dividing rational expressions problem, first step, rewrite the problem as multiplication by keep, change, flip. Keep the first expression the same, nothing changes. Change the division to multiplication, and then flip or take the reciprocal of the second expression. From here, it works out the exact same way as the multiplication problem. Factor if you can factor, and then cancel out any common factors you might find. Okay. The first expression actually can't be factored anymore. That's x plus 9 over x minus 7, nothing else to do. For the second expression, remember 7 minus x, that's the same as negative x minus 7. Keep that in mind. And I wrote it that way because we have an x minus 7 in the other denominator. So those will end up canceling out. And then 81 minus x squared, that's 9 minus x times 9 plus x. All right, then stuff cancels. The x minus 7's cancel, but we still have that negative in the numerator. The 9 plus x's cancel. And finally, we're left with am I tripping? No, I'm not tripping. All right, finally, we will be left with negative 1 over 9 minus x. Now, if you want to, for the 9 minus x, just like we did for the 7 minus x, you can rewrite this. You can say this is negative 1 over negative x plus 9, yes. Or x minus 9, I'm sorry, x minus 9. And then that would be 1 over x minus 9. So you can leave it like this, or if you left it like this, that would be fine too. But you could factor out another negative and make it positive. Or we can factor out the 4, and then we have an x squared minus xy plus y squared. All right, so that's times 24 over x plus y times x minus y. All right. Now, what cancels? Well, 1, I could have factored the numerator with that 24 a little bit better. 24, there's a 4 in the denominator, so I'll say that this is 4 times 6. And then we'll see that the 4 in the denominator cancels with the 4 in the numerator. The x plus y cancels with the x plus y here. And then the x squared minus xy plus xy or plus y squared cancels with the x squared minus xy plus y squared there. All right, lots of stuff canceled. What's left? We have a 6 and an x minus y. So this would be equal to 6 over x minus y. All right, last one. Ooh, what's going on here? We have 4a squared b squared minus 4ab plus 1. Okay, over 2a minus 1 divided by a minus 2a squared b. So 4a squared b squared minus 4ab plus 1 over 2a minus 1 times 1 over a minus 2a squared b. Something's got a factor here. Let's see. So for this first one, this is just 4ab all squared. Okay, let's start with the second denominator. 1 over a minus 1 minus 2ab, okay? Then for that second denominator, we have an 2a minus 1. Yeah. Can't factor out anything else from that. And then for this numerator, all right, let's see how this is going to factor. So we end up with 2ab squared plus 1. I think this would be a 2ab minus 1 times 2ab minus 1. So this term and this term can be canceled because they are opposites of each other, and we'll get a negative 1 from it. And then that's it, nothing else. All right, so when these cancel, we get a negative from them. So I'll put the negative out front. we have a negative and then a 1 in the numerator. I'm sorry, not just a 1, a negative 2ab minus 1 in the numerator and a 2a minus 1 in the denominator. So as you can see with rational expressions, for multiplying and dividing them and simplifying them, it relies heavily on us being able to factor. So those factoring techniques that we learned in chapter 5, keep on saying it, they keep coming back over and over. So make sure you study them.